There is a place on this earth where the silence is so complete, so absolute, that it feels less like an absence of sound and more like the presence of something else entirely. Something patient, something ancient, something waiting. The Sahara Desert stretches across the northern face of Africa like a vast, unbroken exhale. 9 million square kilometers of sand, stone, and sky. It is the largest hot desert on the planet, and from the window of a plane flying high above it, it looks exactly like what most people assume it has always been: a wasteland, a void, a place where nothing grows, nothing lives, and nothing has ever been built. That assumption is wrong. And the degree to which it is wrong is one of the most quietly astonishing things science has uncovered in the last century. 12,000 years ago, the Sahara was green. Not metaphorically green, not partially green, genuinely, abundantly, almost impossibly green. Rivers ran through valleys that are now dry trenches of compressed dust. Lakes stretched for hundreds of kilometers across plains that today produce nothing but shimmering heat. Forests of acacia and ficus rose along ridgelines that now bear only rock and wind-sculpted stone. Hippos swam in rivers that now exist only as faint impressions on a satellite image. Crocodiles hunted in waters that are now buried under 20 meters of sand. Geologists and climate scientists call this era the African Humid Period. Others call it the Green Sahara. It lasted from roughly 12,000 years ago until approximately 5,500 years ago, a window of nearly 7 millennia, during which the most forbidding desert on Earth was, in fact, one of the most livable landscapes on the planet. The monsoons that today barely graze sub-Saharan Africa once swept deep into the heart of the continent, driven by subtle but powerful shifts in the Earth's orbital path around the Sun. More rain fell here, in what is now a landscape of pure desolation, than falls today in large parts of France, and people lived here, not in small, scattered groups clinging to the margins of a harsh environment, but in settled, thriving, culturally rich communities. They raised animals. They cultivated plants. They painted on the walls of rock shelters with an artistic precision and emotional depth that rivals anything produced by any civilization in any era. They were, by any reasonable definition, civilized people. And now, beneath the sand that eventually swallowed everything they built, something has been found. Something that no one expected. Something carved in stone, buried in darkness, and preserved, with devastating perfection, for 8,000 years. There are channels beneath the Sahara. Channels that run for hundreds of kilometers without break. Channels that turn at precise angles, descend at calculated gradients, and connect to holding basins positioned with an engineer's deliberate eye. Channels that moved water, enormous, controlled volumes of water, across a landscape that once had water to move. They were not cut by rivers. Rivers meander. Rivers follow the path of least resistance, curving and bending with the whims of gravity and geology. These channels are different. They run straight where they need to run straight. They curve only where the terrain demanded it. They were designed. They were built. And for 8,000 years no one knew they were there. The largest desert on Earth was once covered in rivers. And someone, thousands of years ago, built a system to move them. A system so precise, so vast, so technically sophisticated, that when scientists finally found it, the first instinct of more than one researcher was to check whether their instruments were working correctly. They were. This is that story. It begins, as so many of the world's most important stories do, not with a discovery, but with a question that someone was finally brave enough to ask. In the autumn of 1981, a space shuttle called Columbia made its second voyage into orbit. Among the instruments it carried was a device that was not, in any formal sense, designed for archaeology. The shuttle imaging radar, Sahara, was built to study geological formations. Its purpose was to map the surface of the Earth in ways that ordinary cameras could not, using radar waves instead of light to see through cloud cover and atmospheric haze. It was a practical tool for a practical, scientific mission. No one on the research team was expecting it to rewrite history. But radar, it turns out, has a peculiar relationship with dry sand. In wet environments, radar waves bounce off the surface and return to the sensor, producing images of what sits on top of the ground. In extremely dry environments as arid as the Sahara, those same waves penetrate the surface. They travel downward through the sand, bounce off the denser material below, and return carrying information about what lies beneath. The drier the environment, the deeper the penetration. In the central Sahara, where rainfall is effectively zero for decades at a time, the radar waves from the Sahara instrument were reaching several meters below the surface and bringing back images that nobody had ever seen before. When the data was processed and the images were rendered, the researchers saw lines. Long, dark lines cutting through the pale geological baseline of the Egyptian and Libyan deserts. The lines were consistent. They were continuous. They ran for extraordinary distances without significant interruption. The initial interpretation was cautious and scientifically conservative. These were likely ancient riverbeds, remnants of drainage systems that had been active during wetter periods in the Sahara's climatic history. That interpretation was partially correct. But it was also, as subsequent decades of research would reveal, profoundly incomplete. Because those lines were only the beginning. As satellite technology improved through the 1990s and into the 2000s, more surveys were conducted. More lines appeared. Ground-penetrating radar studies added resolution to what the orbital sensors had sketched in rough outline. And slowly, with the gathering weight of accumulated data, something began to seem wrong. Wrong in the most interesting possible way. Natural riverbeds do not behave the way these features were behaving. Ancient rivers carved by rainfall and gravity across millions of years carry the signature of their formation in their shape. They branch, they widen and narrow. They cut irregular courses determined by the random variability of terrain and flow. But several of the linear features being identified beneath the Saharan substrate showed characteristics that defied natural explanation. They ran parallel to each other for distances that stretched beyond any natural explanation. Their depths were consistent in ways that suggested controlled excavation rather than erosion. And in certain areas, they appeared to intersect at junctions, points where 2 or 3 features met in configurations that looked less like geological accident and more like deliberate engineering. The scientists who noticed these things were careful. They were methodical. They published their observations in the restrained, hedged language of academic peer review, noting anomalies without overclaiming their significance. But in the corridors of conferences, in the side conversations that happen when the formal presentations end, a different kind of discussion was taking place. A quieter one, a more unsettling one. Natural formations don't run parallel to each other for 300 kilometers. Fault lines fracture. Geological strata tilt and fold. Ancient riverbeds curve and branch according to the laws of fluid dynamics. But these features did none of those things. They held their course. They maintained their spacing. They behaved, in the blunt language of pattern recognition, like something made rather than formed. Something built rather than eroded. And if that was true, if even a fraction of what the data appeared to be suggesting was real, then the implications were unlike anything the academic world of prehistoric archaeology had previously been asked to consider. The researcher's name rarely appears in mainstream accounts of this story. That omission is not accidental. In the world of academic archaeology, the speed at which a career can be derailed by an unpopular hypothesis is roughly proportional to how significantly that hypothesis threatens the existing consensus. And the hypothesis that began circulating quietly in the early 2000s, that the linear subsurface features of the Central Sahara were not natural, that they were constructed, that they were the remnants of a prehistoric engineering project of continental scale, was not merely unpopular. It was, to many in the field, professionally dangerous to even entertain in print. The resistance was not arbitrary or malicious. It was rooted in a deeply embedded set of assumptions about where complex prehistoric civilization could and could not have existed. Those assumptions had been built up over more than a century of archaeological work, and they were not without logic. The places where archaeology had found the earliest evidence of complex social organization, Mesopotamia, the Nile Valley, the Indus River Basin, shared a common feature. They were, at the time of their florescence, wet. They had rivers. They had reliable rainfall. They had the agricultural foundations that conventional models of civilization require. The Sahara, in its current form, had none of these things. And so the idea that a civilization sophisticated enough to build large-scale irrigation infrastructure had existed in what was now a hyper-arid wasteland seemed to violate everything the academic model predicted. What those assumptions failed to account for was time. Not the short time of recorded history, where the Sahara has indeed been a desert for as long as any written record extends, but deep time, the geological and climatic time in which the Sahara's current arid state is not its default condition, but merely its most recent one. The African Humid Period was not a fringe theory or a speculative hypothesis. It was established science, confirmed by multiple independent lines of evidence, including deep-sea sediment cores, fossilized pollen records, and lake shoreline deposits found far into the desert interior. The Sahara had been green, that was not in dispute. What was in dispute, what required a kind of intellectual courage that not everyone in the field was willing to exercise, was the logical consequence of combining two facts that had never quite been placed side by side with full seriousness. Fact 1. The Sahara was lush, wet, and habitable for approximately 7,000 years. Fact 2. Beneath it lay linear features with engineering consistent characteristics. The researchers who began to connect those two facts found that their grant applications came back with skeptical comments. Their conference papers were received with polite but chilling silence. The peer review process, which is designed to ensure scientific rigor, became instead a mechanism for institutional conservatism, a quiet filter that screened out ideas too large to process without dismantling, frameworks too established to easily revise. The data wasn't wrong. The methodology wasn't flawed. The problem was simpler and more human than that. The world's academic establishment, quite simply, was not ready for what the Sahara was trying to say. And so the Sahara waited. It had, after all, been waiting for 8,000 years. A few more decades made no difference at all. There is a version of this story that begins with a press release and ends with a headline. That version is easy to tell. A machine scanned the desert. A system was found. History was rewritten. But the version worth telling, the version that reveals why this discovery is genuinely different from the cycle of sensational archaeological claims that appear and dissolve every few years, requires spending a moment with the machine itself. Not with its technical specifications, which are dense and uninviting, but with the principle behind it. Because once that principle is understood, everything else in this story becomes not just believable but inevitable. Consider the difference between an X-ray and an MRI. Both are imaging technologies. Both allow a doctor to see inside a human body without opening it. But an X-ray gives you shadows, the outline of dense structures like bone, cast against the softer tissue around them. An MRI gives you something far richer, layers of tissue differentiated by their molecular composition, structures mapped by their chemical properties. A three-dimensional portrait of the interior built not from shadows, but from the magnetic behavior of atoms. The difference is not just resolution. It is a difference in the kind of information being captured. One gives you shape, the other gives you substance. Quantum scanning sits in relation to conventional ground-penetrating radar, roughly as an MRI sits in relation to an X-ray. Traditional GPR sends electromagnetic pulses into the ground and listens for their return. It tells you that something is there. It can give you rough dimensions and approximate depths, but it cannot tell you what that something is made of. It cannot distinguish between a hollow tunnel and a compacted earthen channel. It cannot differentiate between naturally fractured rock and hand-dressed stone. Its images are useful but blunt. Quantum gravimetry, the core principle underlying the scanning technology used in the Saharan surveys, works on an entirely different physical basis. Instead of sending energy into the ground and measuring its reflection, a quantum gravimeter measures the gravitational field of the Earth with extraordinary precision, detecting minute variations in that field caused by differences in the density and composition of subsurface material. Solid natural rock produces a different gravitational signature than a hollow channel carved through that rock. Compacted earthen fill produces a different signature than worked stone. An ancient cistern, sealed and buried, produces a gravitational anomaly measurable to within fractions of a microgal, a unit of gravitational measurement so fine that it can detect the difference between a full and empty underground chamber from the surface above. The technology was developed initially for military applications, specifically for detecting underground bunkers and tunnel networks. and later adapted for mineral prospecting, where the ability to identify subsurface ore deposits without drilling represented enormous commercial value. Its migration into archaeological application was gradual, driven by a small number of geophysicists who recognized that the same capability that found bunkers could find buried walls. For the first time in human history, a machine existed that could look through centuries of compacted sand and read what was written underneath. The question was simply where to point it. The data center where the first full quantum scan results were processed was not in the Sahara. It was in a university building with fluorescent lighting, climate-controlled server rooms, and the specific, focused silence of a space where people are paid to pay close attention. The research team had been expecting the scan to produce interesting geological data. What they had not been expecting, what no one on the team had explicitly prepared themselves to see, was what appeared on the visualization display when the first processed dataset was rendered into a spatial map. The anomaly cluster was flagged automatically by the software. This was routine. The algorithm was designed to identify deviations from baseline geological expectation and mark them for human review. What was not routine was the scale of what had been flagged. The cluster was not a small irregularity confined to a few square kilometers. It covered an area larger than the United Kingdom. Hundreds of discrete anomalies, distributed across the scan zone with a spatial organization that the software's pattern recognition module classified, in the dry language of its output log, as non-random clustering consistent with artificial structuring. The first response was exactly what it always is when a machine produces a result that the human mind is not prepared to receive: the assumption of instrument error. Calibration checks were run. The quantum gravimeters were tested against known geological benchmarks. The processing pipeline was reviewed for algorithmic errors. The dataset was re-rendered from the raw sensor readings. None of these checks found a problem. The data was clean. The anomalies were real. The team requested a second independent scan of the same area, conducted by a different instrument platform with no access to the first dataset. This was standard verification protocol for anomalous findings, a safeguard against the possibility that the first set of results had been contaminated by equipment-specific bias. The second scan was processed independently and rendered without prior knowledge of what the first had shown. When the two maps were overlaid, the match was extraordinary. The anomalies coincided with a precision that left no statistical room for coincidence. What the scans were showing in the undeniable specificity of gravitational data was a network, subsurface channels of consistent width and depth, running in organized directions across the landscape. Points where multiple channels converged, junctions with the geometric logic of designed intersection, not natural confluence. Wider, deeper formations at intervals along the channel paths, positioned at points where the underlying geology suggested the presence of ancient water tables, the footprints of cisterns. And threading through it all, the ghost architecture of an irrigation system that had once, in a world entirely different from this one, carried water across the heart of the African continent. They ran the scan 3 times. Each time the machine showed the same thing. And each time, the room got a little quieter. Numbers, on their own, carry weight but not meaning. The numbers associated with the subsurface network that the quantum scans revealed were extraordinary by any standard. The channel widths, the depths, the distances involved. But it was not the numbers themselves that forced the most serious reconsideration of what this discovery represented. It was the geometry. Specifically, it was what the geometry implied about the minds that had produced it. The channels were not all the same width. They were graduated, broader where they connected to what appeared to be primary distribution points, narrower as they extended outward toward the presumed edges of the network's service area. This graduation followed a precise ratio, one that hydraulic engineers today would recognize as consistent with maintaining flow velocities across branching distribution systems. A wider channel moving a large volume of water at a controlled speed feeds into narrower channels that maintain pressure while reducing volume. Principle fundamental to any functioning irrigation grid, whether ancient or modern. The gradient of the channels, their downward slope, was equally revealing. Over hundreds of kilometers, the channels descended at an angle calculated to keep water moving, without allowing it to accelerate to erosive velocities. The slope was maintained within a range of approximately 0.3 to 0.5%, a figure that modern hydraulic engineers identify as optimal for gravity-fed water conveyance in arid environments. Maintaining that gradient across the kind of varied terrain found in the central Sahara required either extraordinary surveying capability or extraordinary luck. The consistency of the angle across the full mapped extent of the network makes luck an unconvincing explanation. The cistern sites, positioned at points where the quantum scans showed the channels widening into holding basins, were located at aquifer intersection points, places where the underlying geology suggested that groundwater came closest to the surface during the wet season. This was not random placement. A cistern placed at an aquifer intersection maximizes its water capture potential by combining surface channel inflow with direct groundwater seepage. Building a cistern in the wrong location, away from an aquifer or above an impermeable rock layer, wastes the enormous labor investment that a rock-lined holding basin requires. Every cistern in this network was in the right place. Comparisons were inevitable. The Persian Qanat systems, built between 12,500 and 3,000 years ago, used similar principles: underground channels tapping aquifers and conveying water by gravity to surface settlements. The Nabatean water harvesting structures of the Negev Desert, built roughly 2,000 years ago, showed comparable sophistication in capturing and distributing scarce rainfall across arid terrain. The Hohokam canals of pre-Columbian Arizona, among the most studied prehistoric irrigation systems in the Western Hemisphere, covered a comparable area. But the Saharan network appeared to predate all of them, by the most conservative estimates, by 3,000 years, by the most aggressive estimates, by 5,000 or more. The angles were too precise, the gradients too calculated. Whoever built this didn't just understand water, they understood mathematics. And the next question, the question that would drive the documentary's investigation through its next 3 chapters, was not about the system at all, it was about the people. There is a plateau in southeastern Algeria called Tassili Nadje. The name in the Tuareg language means roughly plateau of the rivers, a name that strikes most visitors as absurd, because today the plateau is a landscape of wind-carved sandstone towers and dry, orange-red stone, receiving perhaps a centimetre of rain in a good year. There are no rivers, there is no water. There is, to all visible evidence, nothing alive here that does not have deep evolutionary adaptations for surviving on almost nothing. But on the walls of the rock shelters that honeycomb the plateau's face, shelters carved by wind and time from the soft sandstone, there are paintings, thousands of them, covering rock panels that stretch for kilometers, created by human hands at various points between roughly 10,000 and 2,000 years ago. And what those paintings show is not a desert. They show cattle. Dozens, sometimes hundreds of cattle, rendered in ochre and white and black, with a confident, practiced line that suggests not casual decoration, but a sustained artistic tradition. They show elephants and giraffes, animals that require substantial grassland and water, animals that cannot survive in the landscape that surrounds these paintings today. They show swimmers, actual swimmers, their bodies depicted mid-stroke in a fluid that can only be water, painted on the walls of a rock shelter that now sits 500 kilometers from the nearest river. And they show people, not vague, symbolic human forms, but specific human beings, bodies in motion, engaged in recognizable activities. A woman tending cattle, a group of men gathered around what appears to be a communal structure, children, families, dogs, an entire social world rendered with the kind of accumulated artistic skill that only emerges in cultures where art making is not novelty but a practice, something done regularly, handed down across generations, refined over centuries. These are the people who lived before the sand, and they were not wandering, precarious survivors at the margins of a livable world. The evidence in the paintings, read carefully and without the condescension that prehistoric people have too often received from modern interpreters, shows a society of settled or semi-settled communities with domesticated animals, agricultural ambition, and a rich ceremonial and social life. The Wadi Sura paintings in Egypt add another dimension, elaborate, complex scenes of ritual and community that imply not just population, but organization, leadership, shared belief systems, the invisible infrastructure of social order. These were communities that had every reason to build permanent water infrastructure. Communities large enough to require it, organized enough to construct it, and rooted enough in a specific landscape to invest the enormous labor that a system of this scale would have demanded. They were not footnotes to civilization. In the quantum scan data, with its channels and cisterns and distribution nodes built to serve hundreds of thousands of people across a territory the size of Western Europe, these people appear in their proper role. They were the engineers. In the Sahara Desert of central Niger, one of the most remote and desolate places in the entire Sahara, there is a site called Gabero. It was discovered in 2000 by a paleontologist named Paul Sereno, who was searching for dinosaur fossils and found instead something that stopped his excavation in its tracks. Gabero is a cemetery, not a small one. Not a modest burial ground of a handful of individuals from a transient band of wanderers. It is one of the largest prehistoric cemeteries ever discovered anywhere on Earth, containing the remains of hundreds of individuals, buried with a care and intentionality that speaks directly to the sophistication of the society that interred them. The bodies were placed in deliberate positions. Some were arranged in what excavators describe as sleeping postures, arms folded, knees slightly bent, the posture of rest rather than disposal. Grave goods were found alongside many of the remains. Pottery, carved stone tools, animal bones suggesting food offerings. In several cases, the skeletal remains of what appear to be family groups were buried together. The bones of adults and children arranged in proximity that suggests intentional placement. And in one extraordinary instance, a woman was found buried with 2 children in her arms. A tableau of loss so immediate and so human that it collapsed the 8,000 years between that burial and the moment of its excavation into almost nothing. Gabero sits in the middle of what is now an absolutely inhospitable desert. The nearest reliable water source today is hundreds of kilometers away. But beneath the site, the sediment record tells a different story. Gabero was, at the time of its use, situated on the shore of a substantial lake. The people buried here were not desert survivors. They were lake people, fishermen, possibly. Farmers, almost certainly. Members of a settled or seasonally settled community, wealthy enough in resources and sophisticated, enough in social organization to maintain a burial site of this scale and complexity over multiple generations. The ancient DNA extracted from Gabero's remains added a layer of mystery to the human story that the quantum scan data would later begin to address. The genetic profile of the Gabero population did not match any modern human group. It was distinct from present-day sub-Saharan Africans, from modern North Africans, and from any other regional population in the contemporary genetic record. The researchers who analyzed the data called them a ghost population, a lineage that left traces in the genomes of many present-day African peoples but has no direct living descendants. A civilization that contributed to the human genetic heritage of an entire continent and then, as the desert closed in around it, disappeared. As the Sahara began its long, slow drying around 5,500 years ago, this population migrated eastward toward the Nile, northward toward the Mediterranean, southward into the Sahel. And they carried something with them that no quantum scanner can directly measure, but that the data, read carefully, begins to suggest. The timing is uncomfortable if you hold the standard model of civilization's origins with any emotional investment. The African Humid Period ends. The Sahara begins its decisive desiccation at approximately 5,500 years before present. The evidence for rapid, intensive agricultural development in the pre-dynastic Nile Valley begins appearing with unusual speed at approximately 5,200 to 500 years before present. The first recognizably state-level social organization in ancient Egypt. The political consolidation that would eventually produce the pharaonic civilization emerges from this same period. The alignment of these timelines is not, on its own, proof of anything. But in a scientific investigation, the alignment of multiple independent timelines pointing in the same direction is not nothing. The engineering parallels are the part of this story that most demands careful treatment, because careful treatment is exactly what they deserve. The basin irrigation systems of pre-dynastic Egypt, the earliest agricultural water management structures attributed to Nile Valley civilization, share several conceptual features with the Saharan network. Gravity-fed water conveyance, hierarchical distribution, with larger primary channels feeding smaller secondary and tertiary ones. System placement at points of optimal water capture. These are not exotic design choices. They are the logical solutions to the problem of moving water across flat terrain with minimal mechanical assistance. Similar problems produce similar solutions, and the danger of reading cultural transmission into architectural resemblance is real and well documented in the archaeological literature. But the genetic evidence adds a dimension that pure architectural comparison cannot. The measurable overlap between the genetic profile of the Gabero population and the skeletal remains found at pre-dynastic Egyptian sites is not conclusive proof of cultural transmission, but it does establish population movement. People from the Saharan lakeside civilization reached the Nile Valley. They arrived during exactly the period when the Nile Valley's agricultural sophistication was undergoing its most dramatic acceleration. They came from a culture that, the quantum scans now suggest, had been managing water at a continental scale for potentially thousands of years before their arrival. The possibility being raised here, carefully, with full acknowledgement of its speculative dimensions, is that the agricultural revolution we have attributed to the Nile Valley was not born there. It may have walked there, carried in the practical memory of a population, leaving a world that was dying behind them. The engineers who built the pyramids learned from someone. The quantum scans are beginning to suggest who that someone might have been. Imagine a change so slow that no single generation could fully perceive it, but so absolute that its end result was the transformation of a living world into a dead one. Not a catastrophe in the Hollywood sense. No asteroid, no volcanic eruption, no sudden flood, just a gradual, relentless subtraction, a little less rain each decade. The rivers a little shallower each year. The grasslands retreating, centimetre by centimetre, season by season, until the green edge of the habitable world was somewhere your grandfather remembered, but your children would never see. This is what happened to the Sahara. And understanding how it happened requires a brief and humbling encounter with the scale of the forces that govern Earth's climate over geological time. The Earth does not orbit the Sun in a perfect circle. Its path is an ellipse, and that ellipse changes shape over cycles of approximately 100,000 years, stretching from nearly circular to more elongated and back. Again, the Earth's axis of rotation is not perpendicular to its orbital plane. It tilts, and the degree of that tilt varies over a cycle of roughly 40,000 years, and the direction in which the axis points, its orientation relative to the stars, also changes, rotating in a slow wobble over a cycle of approximately 26,000 years. These three overlapping cycles, collectively known as the Milankovitch cycles after the Serbian mathematician who calculated them in the early 20th century, determine, over thousands of years, how much solar energy reaches different parts of the Earth's surface at different times of year. 10 to 12,000 years ago, the configuration of these cycles was such that the northern hemisphere received significantly more solar energy during its summer months than it does today. More summer heat over the African landmass meant more evaporation from the land's surface, which meant stronger low-pressure systems, which drew the monsoon rains deeper into the continent. The Saharan interior received monsoon rainfall comparable to what falls today in the West African Sahel. Rivers filled, lakes formed, grasslands expanded, and in that green world civilization grew. Then the cycles shifted, imperceptibly, inexorably. The amount of solar energy reaching North Africa began to decline. The monsoons weakened. Each year, they penetrated a little less far north. The process was not uniform. There were wetter decades within the general drying trend, hopeful reversals that may have sustained communities in denial of what the long arc of change was already determining. But the direction was one way. By 5,000 years ago, the Sahara was recognizably the desert it is today. By 4,000 years ago, the transformation was essentially complete. For the civilization that had built the irrigation network, a civilization that had responded to the challenges of water management with a sophistication that commands genuine admiration, the drying represented the ultimate test of everything they had built. The channels had been designed for a world with water to carry. As the water retreated, The system that had been their greatest achievement became, gradually, a monument to a world that no longer existed. They built the most advanced water system the prehistoric world had ever seen, and then the sky stopped cooperating. There is a paradox at the heart of this discovery that deserves more attention than it usually receives. The very force that destroyed the civilization that built the irrigation network is also the reason the network survived. The Sahara's extreme aridity, the hyperarid conditions that make it virtually uninhabitable today, created precisely the preservation environment that kept 8,000-year-old carved stone channels in a state of near-perfect condition through 8 millennia of geological time. Consider what happens to buried structures in a moist environment. Water seeps through the soil and into any cracks in stone or mortar. Freeze-thaw cycles expand those cracks. Microbial communities colonize the organic material, bonding the stone together. Tree roots seek water and pry apart anything in their path. Over centuries, moisture is the universal solvent of buried archaeology. It is why excavations in temperate and tropical climates so rarely find ancient stone, structures intact below the soil surface. The Sahara offers none of these destructive agents. Rainfall is effectively zero for decades at a time. Temperature fluctuations, while extreme, occur above the insulating layer of sand that covers the channels, dampening their effect on the buried structures below. Microbial activity is minimal in conditions of near-zero moisture. Root penetration does not occur in a landscape where plants cannot grow. The Aeolian sand that filled and covered the channels, wind deposited in layers of consistent grain size, created a dry, oxygen-limited burial matrix that is, from a preservation perspective, almost ideal. The comparison to Pompeii is not merely rhetorical. Catastrophic events, whether volcanic or climatic, can achieve the same result. The sealing of a moment in time beneath a layer of inert material that stops the normal process of decay. But the quantum scan data revealed something about the channel's burial that went beyond passive preservation. Several junction points in the network, places where primary and secondary channels meet, where the flow volume changes and the structural complexity of the system is highest, showed evidence of deliberate sealing. And stone caps, fitted over the channel openings with the same careful workmanship visible in the channel walls themselves, had been placed across these openings before the sediment burial was complete. The material analysis suggested they were placed intentionally, not deposited by natural processes. This detail does not fit easily into a narrative of sudden abandonment or catastrophic collapse. It fits something more considered, more deliberate, and infinitely more melancholy. Some of the channels were sealed with stone caps before they were abandoned. Someone planned to return. They left their greatest engineering achievement closed but intact, prepared for a resumption of use that the evidence now makes clear never came. The sand settled over the caps, the desert claimed everything above, and 8,000 years passed. The channels themselves are the headline of this story. But the sediment that filled them over the millennia, the fine-grained, layered sand that the quantum scans read as density variation, preserved something beyond the stone walls of the channels themselves. It preserved evidence of how the system was actually used. And that evidence, assembled from multiple independent analytical methods, paints a remarkably detailed picture of an operational irrigation network that was not merely built but actively managed. On the inner surfaces of several channel wall sections exposed during the early excavation trials, microscopic analysis revealed tool marks. Not the random abrasions of rock on rock, but systematic directional marks consistent with the use of standardized stone-cutting implements. Marks that appear in regular patterns, suggesting teams of workers following a shared technique rather than individuals improvising. The angle of the marks, the depth of the cut, and the spacing between tool strokes all point to organized labor, working to a consistent standard. This is not what a small group of motivated individuals leaves behind. This is what an organized workforce under coordinated direction produces. From the sediment layers within the cistern sites, researchers recovered organic material of a particularly informative kind: pollen. Specifically, pollen from plant species that do not occur naturally in the central Saharan region. Species that are domesticated agricultural cultivars, their presence in the cistern sediment explainable only by deliberate cultivation in the fields that the channels once served. millet, sorghum, an early wheat variety whose closest wild relatives grow far to the north and east of where this pollen was found. These plants were grown here because someone planted them, watered them, and harvested them. The channels were not passive natural water pathways serving wild vegetation. They were the arterial system of an agricultural civilization. And at several junction points, within the sediment immediately adjacent to where the quantum scans showed the widening of channels into flow control structures, the preservation conditions had been sufficient to retain faint impressions of organic material with the grain pattern and structural density of processed wood. These are the shadows of sluice gates, the mechanisms by which flow volume was directed into secondary channels or held back to fill cisterns. They no longer exist as physical objects, but their shapes remain, pressed into the mineral record of the sediment around them, as legible as footprints in dried mud. The sand didn't just bury the system. It preserved a fingerprint of every hand that built and used it. There is a particular kind of scientific courage that rarely makes it into the public narrative of discovery. It is not the dramatic courage of a dangerous moment, the physical bravery that popular storytelling finds easy to romanticize. It is quieter and, in some ways, harder to sustain. It is the courage of betting your professional credibility on something that most of your peers believe is wrong, and doing so not in the heat of a single decisive moment, but over years of careful, underfunded, often thankless work. The team that assembled to conduct the first ground truth expedition into the Central Saharan Anomaly Zone was composed of this kind of courage in several different forms. The quantum geophysicist leading the scanning operation had spent the better part of a decade adapting military origin, gravimetric technology for subsurface archaeological application, work that most of his departmental colleagues considered an eccentric distraction from more fundable research directions. He had presented his methodology at 3 international conferences before a single archaeology department expressed meaningful interest. He had self-funded 2 preliminary scan surveys from discretionary research budgets that his university had allocated for other purposes. The paleohydrologist on the team, a specialist in the behavior of ancient water systems in arid environments, had published 2 papers arguing for the existence of large-scale prehistoric irrigation infrastructure in the Saharan basin, before the quantum scan data existed to support her conclusions. Those papers had been received with a mixture of polite skepticism and pointed criticism. She had continued regardless. The team also included remote sensing analysts, paleoanthropologists, a sediment dating specialist, and, critically, a group of Tuareg guides whose knowledge of the Central Saharan landscape was as practically indispensable as any piece of equipment the expedition carried. Operating across 3 sovereign nations, in regions where the authority of national governments extends only theoretically, and the reality on the ground is considerably more complex, the Tuareg guides provided not just navigation but negotiation. Their relationships with communities in the expedition zone were the difference between a team able to work and a team unable to proceed. The conditions the expedition faced were not the conditions of a controlled research environment. Ground temperatures in the Central Sahara in summer exceeded 50 degrees Celsius at the surface. Temperatures at which electronic equipment malfunctions, at which human cognitive performance begins to degrade, at which the body's cooling mechanisms are operating at their physiological limit. Sandstorms descended with little warning and blanketed visibility to 0 within minutes, while depositing fine abrasive particles into every unprotected electronic interface. They were going into one of the most dangerous regions on Earth to find something that most of their colleagues still didn't believe existed. They went anyway. The first excavation site was selected based on 3 converging pieces of data: the density of the quantum scan anomaly at the target coordinates, the relative accessibility of the location within the expedition's operational range, and, though this was not formally recorded in the expedition logs, the intuition of the lead Tuareg guide, a man whose family had crossed this particular stretch of desert for 5 generations, and who, when shown the scan anomaly map, pointed to the target coordinates and said something that was translated later as, "This is where the ground sounds different." What that meant in practical terms no one fully understood until the excavation began. The first trench was opened at dawn, when the temperature was still tolerable and the light was good. The work was methodical and deliberate, not the frantic pace of someone expecting a quick result, but the careful, systematic removal of material that archaeological excavation requires when the stakes of disturbing context are high. The upper layers of sand yielded nothing unusual. Wind-deposited aeolian deposits, consistent with the standard Saharan stratigraphy that the team's sediment specialist had predicted. At 4 meters of depth, the sediment character changed. The loose aeolian sand gave way to a more compacted layer, denser, slightly darker, with a different resistance to the excavation tools. At 6 meters, the temperature inside the trench had dropped noticeably from the surface. At 10 meters, the sediment specialist noted a layer of fine organic material, decomposed plant matter pressed flat against what appeared to be a harder surface below. At 12 meters, a research assistant's brush touched something that stopped her hand. The surface was smooth, not the variable, granular smoothness of natural stone shaped by geological process, but the precise, even smoothness of a surface that had been worked, dressed, cut to a flat plane with intent and skill. More of the surrounding sediment was carefully removed. The surface extended. It continued outward in both directions from the initial contact point, with a consistency that made the natural explanation not just unlikely, but geometrically impossible. At the depth of 12 meters in the absolute center of the Sahara Desert, in a region that conventional archaeology had classified as archaeologically negligible, the expedition team had touched the wall of an ancient irrigation channel. The dimensions matched the quantum scan projection to within 2%. No one celebrated. The kind of silence that falls when something you were almost afraid to believe turns out to be absolutely real is not a silence that celebrates. It absorbs. When an archaeological discovery is made, the initial find is rarely the final statement of what the discovery actually represents. The first unearthed shard is a promise. The full excavation is the answer. And in the case of the Saharan irrigation network, the distance between the first confirmed channel wall at 12 meters depth and the answer to the question of what the full network actually comprised was a distance that took months of additional scanning, analysis, and verification to begin to cross. The quantum scan data, processed sequentially as the expedition extended its survey area, produced a map that grew with each new dataset in a direction that consistently outran the team's expectations. The primary channel network, the main arterial channels connecting the system's major nodes, extended approximately 2,400 kilometers in total length. There were an estimated 140 major cistern sites distributed along the network at the positioning intervals original anomaly analysis had predicted. The distribution node structures, the junction points where flow was divided between primary and secondary channels, numbered in the hundreds, each one representing a point of managed water allocation serving the communities downstream. The system was designed to serve a population. The flow capacity of the primary channels, calculated from their cross-sectional dimensions and their gravitational gradients, suggested a total water delivery volume sufficient to support intensive agriculture across a territory comparable in area to modern Western Europe. Population estimates derived from those agricultural capacity figures placed the civilization that used this system somewhere between several 100,000 and a number that, spoken aloud in a research presentation, prompted one senior geophysicist in the audience to ask that it be repeated. The number was not repeated, it was written down, and it sat in the notes of everyone who heard it for a long time afterward. The comparison that placed this scale in sharpest relief was the Mesopotamian canal system. The canals of ancient Mesopotamia, the engineering achievement to which almost all modern assessments of prehistoric hydraulic infrastructure ultimately defer, covered a comparable area at their maximum extent. But the Mesopotamian system was built over 2,000 years of continuous civilization, expanded incrementally by successive states with accumulated engineering traditions and growing organizational capacity. The Saharan network appeared, in the quantum scan data, to have been built within a far more concentrated period. The sediment dating evidence suggested construction was not incremental but relatively rapid, implying a level of initial planning and organizational coordination that the Mesopotamian comparison makes more, not less, remarkable. When they mapped the full extent of the network, the lead geophysicist sat back in her chair and said nothing for 4 minutes. Then she asked for the hard drive with the raw data. She wanted to look at it again from the beginning. There is a theory in the history of human civilization, controversial, contested, but stubbornly persistent, that large-scale irrigation is not just a product of complex societies, it is a producer of them. The German-American historian Karl Wittfogel articulated this idea most forcefully in the middle of the 20th century, arguing that the management of large water systems too big for any individual community to control, too critical for any community to risk losing, inherently creates the conditions for centralized authority. Whoever controls the water controls the survival of every person connected to the network. That kind of power does not remain distributed. It concentrates. Wittfogel called civilizations built around this dynamic hydraulic civilizations, and his theory has had a complicated academic life, embraced, critiqued, partially rehabilitated, partially rejected, and ultimately left in the awkward position of being probably partly right without being entirely provable in any specific case. Until perhaps now. The design of the Saharan irrigation network is not neutral. Every engineering choice embedded in its structure carries an implicit statement about the social organization of the civilization that made those choices. The hierarchical channel system, primary channels serving secondary channels, serving tertiary channels, serving individual community distribution points, is not just an efficient hydraulic design. It is the physical embodiment of a tiered authority structure. Water flows from the top down. Decisions about how much water flows to whom and when must also have flowed from somewhere near the top. The system placement data is particularly revealing in this regard. Not all cisterns in the network are equal. Some are large, capacious enough, by the quantum scan's volumetric calculations, to hold reserves sufficient for an entire growing season in a major agricultural district. Others are small, local, limited in capacity. The distribution of large versus small cisterns across the network's geography does not follow a pattern of equal distribution. It follows a pattern of hierarchy. Certain locations received far more water storage capacity than their position in the landscape alone would demand. These were not just towns or villages with a water supply. These were nodes of power in a network whose physical architecture encoded the social order of the civilization that built and managed it. Control the water, control the people. Whoever designed this system understood that equation 10,000 years before the first pharaoh was crowned on. Every network has a source. Every system of distributed control has a point from which control is exercised. The quantum scan data, for all its extraordinary detail, has not yet revealed that point directly. But it has done something almost as informative. It has identified the candidates. And the process of identifying them illuminates, in its own way, what must have existed even before the evidence is found. In a gravity-fed hydraulic network, water flows from high to low. The source of the network, the point from which the primary channels emanate, must be either at a natural elevation or at the location of the primary water intake, the place where the system connects to its original water supply. In the Green Sahara, that supply was the rain-fed river system of the African Humid Period. The quantum scan data shows 3 locations where multiple primary channels converge in ways that suggest proximity to the original water source. 3 candidate sites for the administrative and perhaps residential center of whatever governing entity managed this system. The first candidate is in the Tibesti mountain region of northern Chad. The Tibesti Massif is the highest terrain in the Sahara, a volcanic range whose peaks exceed 3,000 meters and whose geology has kept the substrate relatively undisturbed by the aeolian processes that have reshaped the lower desert around it. The quantum scan anomalies in this area are dense and complex, suggesting structural remains not just of channels, but of more substantial above ground architecture. The second candidate is in the Fezzan region of southwestern Libya. This is, in retrospect, a location of considerable archaeological interest independent of the quantum scan results. The Fezzan was, in historical times, home to the Garamantian civilization, a confirmed hydraulic society whose sophisticated Qanat systems are one of the established wonders of ancient. North African engineering. The possibility that the Garamantes built their civilization on ground already shaped by a much earlier water management culture, inheriting not just a landscape but a physical infrastructure, is one of the most quietly electrifying implications of the broader discovery. The third candidate is in northeastern Niger, where the scan data suggests not just channels but an anomaly cluster that the pattern analysis module flags as potentially consistent with the footprint of a large settled structure, something more architecturally complex than a simple cistern or junction point. This site has not yet been excavated. Every water network has a source. Every empire has a capital. The quantum scans suggest they haven't found it yet, but they know exactly where to look. Ideas do not die with the people who hold them. This is one of the most fundamental truths about human civilization, and it operates across timescales that challenge the imagination. A building technique developed in one generation is taught to the next. A water management principle discovered by one community is adopted by a neighboring one. Knowledge is the most durable thing human beings have ever produced. More durable than stone, more durable than bronze, more durable even than the civilizations that originally generated it. And the engineering knowledge embedded in the Saharan irrigation network is, in the context of this story, particularly interesting to trace. The Persian Qanat system, arguably the most celebrated ancient hydraulic engineering tradition in the historical record, shares a striking set of design principles with the sub-Saharan network. Underground channels convey water from highland aquifer zones to lowland agricultural areas entirely by gravity, with no mechanical pumping. The channels maintain a precise gradient calculated to keep water moving without causing erosive velocities. Vertical access shafts at regular intervals allow maintenance and also serve as pressure relief points. The system is designed to minimize evaporation by keeping water underground for as much of its journey as possible. These features appear in both the Persian Qanat tradition and in the Saharan network. And the Saharan network is older by a margin of several thousand years. The Falaj systems of ancient Arabia and Oman show comparable design logic, as do the Foggara systems of the Saharan Berber communities and the Qattara systems of Morocco. All of these traditions have been studied as independent innovations, parallel developments of similar solutions to the similar problem of moving water through arid terrain. That interpretation remains defensible, but the timeline now presses against it. If the earliest known expression of underground gravity-fed irrigation existed in the prehistoric Sahara, and if the population of that region dispersed eastward and northward as the Sahara dried, then the geographic arc of their migration overlaps almost perfectly with the geographic distribution of every subsequent arid land hydraulic tradition in the Old World. The same engineering principles, the same gradient calculations, separated by 3,000 years and 2,000 miles. Coincidence or memory? The story of human civilization, as it is taught in schools and presented in mainstream historical accounts, begins in Mesopotamia. Around 5,500 years ago, in the river valleys between the Tigris and the Euphrates, the first urban settlements emerged with sufficient complexity to qualify as what historians call states. Organized political units with specialized labor, administrative hierarchies, written language, and monumental architecture. Within a few centuries, Egypt and the Indus Valley had followed independently along comparable trajectories. From these three hearths, the narrative of civilization spread outward across the world. This narrative is not fabricated. It is based on the best available evidence assembled over more than a century of archaeological work concentrated in those regions. But it is also, in the most precise technical sense, an artifact of where archaeologists have chosen to dig. And archaeologists, like all humans, tend to look where they expect to find things. The expectation that complex civilization emerges from river valleys in temperate and semi-arid zones, rather than from hyper-arid zones that were, at the relevant time, neither hyper-arid nor uninhabited, has shaped every research agenda, every grant proposal, and every syllabus in the discipline for generations. It has produced an enormous body of knowledge about the places where archaeology has looked. And it has produced silence about the places where it has not. The Saharan discovery does not fit cleanly into this narrative. not because it contradicts everything the existing evidence says about Mesopotamia, Egypt, and the Indus Valley. It does not. Those civilizations were real, their achievements were extraordinary, and the timeline of their development is well supported by extensive evidence. What the Saharan discovery challenges is the assumption that civilizations represent the beginning of the story rather than a middle chapter. If a civilization capable of coordinating the construction and management of a continental-scale irrigation network existed in the Central Sahara 8 to 10,000 years ago, then the cognitive capacities, social organizational structures, and engineering traditions required for complex civilization were already present and already operating millennia before Mesopotamia's first cities were founded. This is not a minor revision, it is a reframing of the entire arc of the story. Göbekli Tepe in Turkey, a monumental ritual complex built 12,000 years ago by people who were supposedly pre-agricultural, had already introduced a crack in the standard model, demonstrating that the organizational capacity for large-scale communal construction predated settled agriculture in at least one documented case. The Gunung Padang site in Indonesia has added further pressure. The Saharan discovery, if its construction date is confirmed at the most conservative estimate, adds a structural failure that the standard model cannot repair with minor adjustments. The textbooks say civilization began 5,500 years ago. The Sahara is asking for a recount. The institutional response to genuinely paradigm-altering discoveries follows a pattern that is almost embarrassingly predictable once you have seen it enough times. There is initial dismissal, conducted with the cool authority of established expertise. There is a period of methodological challenge, during which critics focus not on the conclusion but on the quality of the evidence. A legitimate and necessary phase of scientific scrutiny that is sometimes, in practice, used primarily as a delay mechanism. There is a phase of fragmented acceptance, during which individual elements of the new claim are incorporated into the existing framework, while the most disruptive implications are held at arm's length. And eventually, if the evidence continues to accumulate, there is a renegotiation of the framework itself, a process that can take generation and that is rarely acknowledged as the paradigm shift it represents, until historians write about it decades later. The Saharan quantum scan data is currently somewhere in the middle of this sequence. The methodological challenge phase has been substantive and in several respects legitimate. The specific criticisms that carry the most weight in the technical literature concern three areas: direct dating of the construction event, ruling out all natural geological processes, and reconciling the scale of the network with what is known about prehistoric population density in the region. These are not trivial objections, they are the right questions to ask. But questions are not the same as answers. And in this case, the answers that have emerged have made the debate more interesting, not less. The geophysicists behind the scan methodology have defended their instrument calibration records, pointing out that the same quantum gravimetry systems have been used successfully in mining, tunnel detection, and subsurface utility mapping with extremely low false positive rates. They are not asking anyone to abandon skepticism. They are asking critics to apply the same skepticism to the possibility of natural explanation that they apply to the possibility of human construction. Meanwhile, a younger generation of archaeologists and remote sensing specialists has become increasingly open to the data, if not yet to the boldest interpretations. For them, the discovery is less a threat than a challenge, an invitation to expand the map of prehistoric complexity beyond the regions that have dominated academic attention for the last century. The disagreement is real, the stakes are high, but what is happening in the field is not a rejection of science. It is science in its most uncomfortable and useful form. The moment when evidence arrives before consensus is ready to receive it. And somewhere underneath that institutional debate lies the simpler fact that the ground itself does not care what anyone thinks. The channels are still there. The systems are still there. The geometry remains. A theory can be argued with. A buried structure cannot. Dating a buried structure is never as simple as dating the culture that built it. Stone can be moved, sediment can be redeposited, organic material can drift into places it did not originally belong. Archaeology lives with uncertainty, and honest archaeology does not pretend otherwise. That is why the age question in the Saharan discovery matters so much. The more carefully it is handled, the stronger the eventual conclusion becomes. Several dating methods have now been applied to the buried sections of the irrigation network. Optically stimulated luminescence, or OSL, has been used to determine when the sediment around the channels was last exposed to sunlight before burial. Because quartz and feldspar grains accumulate trapped energy from background radiation over time, scientists can estimate the last time those grains saw daylight by measuring the stored signal. In the Saharan samples, the burial layers above the channels consistently return dates between 7,200 and 8,400 years before present. That does not tell us exactly when the channels were built, but it does tell us that they must have been in place before the burial event occurred. Radiocarbon dating of organic material recovered from cistern sediments has produced complementary estimates, though with wider error ranges. Some of the oldest samples suggest the system may have been in use several centuries before the channels were finally sealed by sediment. Paleoclimatic correlation offers another layer of confidence. The architecture of the network makes most sense in the wetter portion of the African Humid Period, when the Sahara still supported large water systems. The engineering would have been pointless after the regional hydrology collapsed. So the construction window almost certainly falls before the onset of major drying, placing the system squarely in the late Neolithic period. The conservative conclusion, the one that can be defended without overreaching, is already extraordinary. The irrigation network is at minimum 7,000 years old. That alone makes it older than the Great Pyramid by more than 2.5 millennia. Older than the first dynastic kings of Egypt. Older than the commonly taught beginning of urban civilization in many parts of the world. But there is a stronger possibility, still not proven, that the first channels may have been laid down earlier, perhaps much earlier, during a wetter phase of the Green Sahara when permanent settlement first became possible. If that turns out to be true, then the story deepens again. Because what has been found would not simply be one of the oldest large-scale irrigation systems ever discovered. It would be one of the oldest durable expressions of organized human engineering on the continent. There is a strange imbalance in the way the world tells its own history. Some regions appear in every introductory survey, every documentary series, every museum narrative, while others are treated as if they emerged only when the outside world noticed them. Africa has suffered from this imbalance, more than almost any other place on Earth. Not because it lacks historical depth, it has more of that than most regions, but because the frameworks used to study history were built during an era that did not know how to see Africa clearly. Colonial scholarship did not simply overlook African civilizations. It actively struggled to imagine them on equal terms with the better-known river-valley societies of Eurasia. The assumption, often unstated but constantly reinforced, was that complexity arrived in Africa from elsewhere, or that wherever it appeared locally, it was somehow derivative, delayed, or incomplete. That assumption shaped what was funded, what was excavated, and what was considered worthy of serious attention. The Saharan discovery pushes directly against that legacy. The more data the scans reveal, the harder it becomes to maintain the older idea that the African interior was historically peripheral to the development of civilization. The opposite may be closer to the truth. The Sahara was not empty space. It was a populated, dynamic, environmentally changing landscape where people developed sophisticated strategies for survival and infrastructure. It was a corridor of migration, a center of innovation, and possibly one of the earliest places on Earth where human beings built systems large enough to reshape entire regions around the management of water. Africa contains some of the oldest geological formations on the planet and the deepest record of human habitation anywhere in the archaeological record. It is the continent where our species emerged, diversified, and repeatedly adapted to changing worlds. It should not be surprising, then, that it also contains hidden chapters of engineering and social organization that predate the canonical origin, stories told in most classrooms. The surprise is not that such a civilization existed there. The surprise is how long it took to look. The Saharan irrigation network does not diminish the achievements of later African civilizations. It does something more interesting. It expands their context. It suggests that the great hydraulic traditions of North Africa and the Sahel were not isolated flashes of genius, but part of a much longer continuity of knowledge, rooted in prehistoric adaptation to changing water regimes. The Garamantian civilization of Libya is the clearest example. Long known for its sophisticated Fagara systems, underground water channels designed to tap fossil aquifers and convey water to oases in the desert. The Garamantes were once treated as an impressive but relatively late regional culture. The Saharan discovery changes that picture. Their engineering suddenly looks less like a local invention and more like a revival, a memory carried forward across generations from a much older source. The physical landscape they inhabited may itself have preserved older infrastructure beneath later layers of use. Farther south, the agricultural systems of the Niger inland delta reveal a different but related pattern. In a region where seasonal flooding created both opportunity and constraint, ancient communities developed methods of managing water that balanced ecological sensitivity with large-scale productivity. The sophistication of these systems has long been recognized by specialists. What the Saharan discovery adds is a deeper lineage, a possible ancestral tradition of hydraulic reasoning that predates the better-known state formations of the medieval Sahel by thousands of years. The Horn of Africa tells yet another story. Long before the rise of Aksum, communities in the region were already working with irrigation-based agriculture, terracing, and water capture systems that reflected serious environmental intelligence. If the Saharan network is the earliest known large-scale expression of that intelligence, then these later cultures can be seen as part of a broad African tradition of adaptation to water scarcity and climate change. Not derivative, not secondary, continuous. What changes here is not only chronology, it is dignity. The idea that Africa's great civilizations stood on the margins of world history dissolves when history is examined more carefully. They were not margins, they were foundations. A buried civilization does not belong to the people who first scan it from orbit, nor does it belong solely to the scientists who confirm its existence. And when a discovery spans several modern borders, the question of ownership becomes more than academic. It becomes political, cultural, and deeply human. The Saharan irrigation network runs beneath territory that now belongs to Libya, Chad, Niger, Algeria, and, depending on how the broader hydrological system is eventually mapped, potentially parts of Sudan and neighboring regions as well. Each of these nations has a legitimate claim to participation in the research, interpretation, and stewardship of the site. International science thrives on collaboration, but cultural heritage cannot be handled as if the land beneath modern borders were politically neutral. It is not. There is also the question of the people who have lived with the desert for generations. Tuareg and Tubu communities know this landscape in ways no satellite ever could. Their oral traditions, travel routes, and place-based memory are not decorative additions to the scientific process. They are part of it. When elders speak of underground water, lost pathways, or old places where the ground behaves differently, they are not always speaking metaphorically. Sometimes they are preserving knowledge that formal institutions forgot to preserve. Modern heritage law tries to balance these issues through frameworks, such as UNESCO conventions and national antiquities policies. Those frameworks matter. They protect against looting, reckless excavation, and the extraction of artifacts into private or foreign collections. But no legal framework can fully settle the deeper ethical question, which is this. What does it mean to uncover a civilization that was never forgotten by the land, even if it was forgotten by the people who wrote the textbooks? For now, the most responsible answer is collaboration, shared research, shared stewardship, shared recognition that the story beneath the Sahara is not a national trophy and not a colonial prize. It is a human inheritance, waiting under sand that has not yet finished giving up its secrets. The discovery is not finished. In many ways, it has barely begun. What the quantum scans have done is reveal a pattern. What the excavation teams are now attempting is to turn that pattern into a chronology, a social map, and eventually a historical narrative with names, dates, and functions attached to the stone. The next phase of research is built around three broad objectives. The first is targeted excavation of the most promising candidate administrative center sites, the points where the network's primary channels converge, and where the above-ground anomalies suggest a settlement of some kind once stood. If archaeologists can find evidence of urban-scale architecture, storage facilities, ritual structures, or inscriptions at these locations, the question of centralized governance will move from inference toward demonstration. The second objective is expanded scanning coverage. The initial survey mapped only part of the network. There are still gaps between the already confirmed segments, and those gaps may conceal tributary channels, secondary waterworks, or even more important structures than the main arteries currently known. As scanning technology improves and costs fall, the team plans to extend coverage farther into less accessible regions of the Central Sahara, where some of the most significant unknowns may still be buried. The third objective is environmental DNA and soil core analysis from cistern and sediment sites. This is perhaps the most exciting scientific frontier in the whole project. Environmental DNA, or eDNA, can preserve traces of plants, animals, and even microbial communities long after the original organisms are gone. If the cistern sediments contain usable eDNA, researchers may be able to reconstruct the crops, livestock, and surrounding ecology of the civilization that used the network. It would be possible, for the first time, to say not just how they moved water, but what they grew with it. There is also technological momentum behind the discovery. The quantum gravimeters used in the initial surveys are being refined for greater portability and lower energy consumption. Drone-mounted versions are already under development. If they succeed, the cost of conducting large-scale subsurface surveys in extreme environments will fall dramatically. The Sahara may turn out to be only the first landscape where this method changes the map of human history. Most people imagine ancient history as distant primarily because of the dates. 10,000 years feels remote, but in another sense, the distance is not temporal, it is psychological. We assume ancient people were fundamentally different from us, less reflective, less analytical, less capable of abstraction. Discoveries like the Saharan irrigation network quietly dismantle that assumption. The cognitive leap required to build such a system is not trivial. Someone had to understand elevation and gradient. Someone had to coordinate labor across distance. Someone had to plan for seasonal variation, storage, maintenance, and flow control. Someone had to think not in days or weeks, but in years and generations. These are not primitive mental acts. They are the acts of human beings who recognized the world as a system of interconnected parts and acted accordingly. That realization changes the meaning of antiquity itself. It suggests that the people we call ancient were not the early, underdeveloped versions of us. They were us, or something very close to us, living under different sky conditions, in different landscapes, with different constraints. They were inventive because they had to be. They were patient because survival demanded it. They were builders because the world around them was changing, and they knew that only structure could hold against change. From that perspective, the Saharan discovery does something larger than extend a timeline. It restores depth. It gives civilization a longer memory. It reminds us that the problem of making life work in difficult environments is not a modern problem. It is an ancient one. And the answers our ancestors found may be older, more sophisticated, and more relevant than we have been willing to admit. Once a method proves itself in one place, the map of possibility expands everywhere else. The Sahara is not the only desert on Earth that may conceal the remains of prehistoric systems hidden from ordinary view. It is simply the first where quantum scanning, climate history, and archaeological persistence have aligned strongly enough to force the question into public consciousness. The Arabian Peninsula is a logical next target. During the same broad climatic window that made the Sahara green, large parts of Arabia also experienced wetter conditions, supporting lakes, grasslands, and human settlement. Recent surveys have already found evidence of prehistoric occupation in areas now considered barren. The possibility that more extensive infrastructure lies buried beneath later aridity is not remote. The Rub al-Khali, or empty quarter, has long been treated as one of the most forbidding landscapes on Earth. But even this vast sea of sand may preserve traces of older hydrological systems, ancient settlement corridors, or the remains of societies that managed water in ways only now becoming visible to modern technology. In western China, the Taklamakan Desert contains buried river systems and relic landscapes that point to a more hospitable past. In South America, the Atacama's extreme dryness makes it another candidate for exceptional preservation beneath the surface. The technology used in the Sahara will not solve every archaeological mystery, but it may begin to reveal a pattern that has been invisible, simply because the method of seeing it did not exist before now. The unsettling and exciting possibility is that the Sahara is not exceptional, it is only first. Beneath the world's deserts may lie a parallel archive of human engineering, a library of lost water systems, abandoned settlements, and forgotten populations whose histories were not destroyed, only sealed away. The Sahara was the first desert we looked at closely. It will not be the last. There is a peculiar humility in the survival of built things. Mountains survive because they are mountains. Monuments survive because people decide to maintain them. But systems built for practical use, drainage channels, roadways, irrigation works, survive only if they are made well enough to outlast the world that needed them. The Saharan irrigation network survived because of a combination of intention and accident. It was built with extraordinary care. Then the climate changed. Then the desert preserved it. What survived was not the society that built it, that vanished. What survived was not even a memory of the system in any formal written sense, because no inscription has yet been found that identifies the builders by name. What survived was the structure itself, the precise gradients, the carved stone, the sealed junctions, the cisterns at the aquifer points. 8,000 years later, these are still legible. There is something almost unbearably poignant about that. These channels were not built to become archaeological wonders. They were built to work, to move water, to keep crops alive, to sustain communities through a changing climate. Every stone was laid in service of a future the builders expected to inhabit. The sealed caps at the junctions reinforce that impression. They did not abandon the system carelessly. They prepared it. They intended continuity. They hoped for return. Instead, the desert remained, and the water became memory. The scale of that memory is what makes the discovery so hard to absorb. A civilization existed here long enough to think in terms of infrastructure, long enough to know how to manage scarcity, long enough to build for generations they would never meet. And then, when the conditions changed, the land buried them so completely that the modern world could not tell they had been there until we built machines capable of listening to gravity itself. Every major discovery has its human story, and this one is no different. Behind the scan results, behind the excavation trenches, behind the maps and the sediment samples and the statistical models, there are people who kept going long after caution would have advised them to stop. The quantum geophysicist who first proposed scanning the Central Sahara had spent years trying to persuade funding bodies that the technology could reveal more than mineral deposits and hidden military structures. He was, for a long time, a man with a good idea and very little institutional enthusiasm. His persistence mattered. The paleohydrologist on the team had spent most of her career arguing that the Sahara's prehistoric hydrology had been underestimated. She had built a professional life around a thesis many people considered too broad, too speculative, or too far outside the mainstream. The discovery did not vindicate all of her claims, but it did something perhaps more valuable. It proved that the question itself had been worth asking. The Tuareg guide, whose family had lived on the edge of the desert for generations, contributed something that cannot be captured in a grant report. He knew which valleys carried wind differently. He knew which dunes changed shape after rain. He knew where the ground seemed to hold sound in a way that felt unusual. When he told the team that the land sounded different at the target site, he was not speaking poetically. He was naming an observation born of deep familiarity. And there was the quiet work of the younger researchers, the trench supervisors, sediment analysts, camera operators, and data processors, whose names will probably not appear in headlines, but whose patience made the entire excavation possible. They were the ones who brushed the stone clean, labeled the samples, logged the coordinates, and kept the record intact when the emotional weight of the find might easily have made less disciplined teams careless. This is how history is actually recovered. Not by a single genius in isolation, but by groups of people willing to listen to what older places are trying to say. In the Sahara, the sand had been speaking for millennia. These were the people who finally learned how to hear it. When people speak of deserts, they often speak as if deserts are empty. But emptiness is a description made from the perspective of not yet understanding. The Sahara is not empty, it is full of time. Full of buried riverbeds, buried lakes, buried paths, buried stories. Full of the record of worlds that rose, adapted, and disappeared without leaving the kind of monuments modern eyes are trained to expect. The discovery beneath the Sahara does not close the story of human civilization. It opens it. It suggests that what we have called the beginning was only the first chapter we happened to discover, not the first chapter that existed. It implies that there may have been earlier forms of organization, earlier forms of engineering, earlier forms of social complexity, all of them erased not by failure, but by climate, not by ignorance, but by changing conditions that even sophisticated societies could not control. And that should not frighten us. It should humble us. Because the real lesson of the Saharan network is not that our ancestors were impossibly advanced. It is that they were human. They studied the land, learned from it, built according to its rules, and tried to make permanence out of an impermanent world. They succeeded longer than anyone expected. They succeeded long enough to be buried. And because they were buried, they were preserved. Because they were preserved, they could be found. Because they were found, the story changes. The Sahara still has more to say. So do the other deserts, so do the oceans. So do the ice sheets and the buried valleys, and the ruins sealed under cities built much later on top of them. The history of our species is larger than the surface record suggests. It always was. We are only now building the instruments to see that clearly. And perhaps that is the quietest wonder of all, that the past did not disappear. It waited. Beneath the sand, the channels are still there. The water that once moved through them is gone. But the memory remains, and the memory, after 8,000 years, has finally begun to speak.